Hello again, friends. It is Ben, and this is a video for the stat class concerning the material we covered in sections 4.3 and 4.4 in the text. Those are the multiplication rule and then some counting rules. Okay. Used to be that this textbook put the counting rules first, but they changed between editions. All right. So I'm going to jump over here to my iPad. Oh, it's giving me options. Hmm. Okay. Let me go ahead and try this as background and we'll see. No, that's not going to work. Let's just do the content then. Share. And then I'm going to put my iPad up here sometime today, eventually. All right. Okay, so what we're talking about here are the multiplication rules. And in this, there's a couple of ideas going on. And I think that your textbook, if I remember right, goes ahead and talks about this first and then this. But I feel like we ought to talk about this here first. So, what I mean by this here is something that's referred to as conditional probability. So, this is the probability of A given B occurs. Okay. So, to get an idea about this, let me tell you a story. I do this a lot, sorry, but a colleague of mine is a gambler who goes to Las Vegas, and he's really good at it. As you can imagine, a mathematician knows about doing a lot of probability stuff, but he's also really good at bluffing and stuff. So anyway, he has been dealt cards in a Texas Hold'em game, and he glances at them, but doesn't really look at them. Okay. So when he glances at them, what he sees is that he has a red queen. And knowing that he has a red queen, there's only two possibilities that that is. And so when he looked at the rest of the cards in the flop, it meant that if he had if he had a queen of hearts, he was going to have a royal flush. This is a hand that is almost never dealt, almost never. You can watch World Series of Poker for 1,000 years and you'll probably never see it dealt. Okay. So he thinks that he's got what did I say? The Queen of Hearts, and that means that he has a royal flush. In actuality, he has the Queen of Diamonds, which means he just has a flush. All right. So the thing that was going on there is that he now has a 1 in 2 chance. From his perspective, he has a 1 in 2 chance of having this royal flush. If he did not have that information, if he had not looked at the card, there's a 1 in 52 chance of getting that card, as opposed to a 1 in 2 chance of getting that card. Okay. So knowing that he had a red queen means that the probability of getting the Queen of Hearts is 1 in 2. But not knowing anything about it, the probability would have just been 1 in 52. All right. So I hope that's a helpful notion there. When we have some information, sometimes it will change the probabilities. So then here, the other big thing in here about that is when we talk about things that are independent. And with regard to that, I'm going to grab this here and push it into the pane there. We need to know that what we mean by independent is that one event does not affect the other. Okay. If I flip two coins, knowing the outcome on one coin is not going to tell me the outcome on the other coin, right? So those two events are independent of each other. That is not to say if one of them is tails, then the other has to be heads or anything like that. There's no coupling between them that excludes something. It's just saying knowing one of them doesn't give you information about the other. If any of y'all are heading towards physics stuff, when they talk about coupling particles, it's not coupling, it's pairing or something. There's quantum, there's quantum stuff that has to do with that sort of thing, where you can set up events that are somehow affecting each other at a distance and stuff. But that's not what we're talking about at all. We're just talking about events that either affect one another because of the information it tells you one thing or the other, or they don't affect one another. Okay. So if the two events are independent, then we can get the probability of having both events occur by just multiplying the probability of each of the events. If I want to talk about flipping a coin and it coming up heads both times, the coin coming up heads on the first throw does not affect the second throw. Okay. On the other hand, if you were drawing cards out of a deck without replacing them, when I draw one queen out of the deck, then when I do this, maybe that's the first draw. Then when I do the second draw, there will be fewer queens in the deck. So it does affect the probability. Okay. So independent is not the same as mutually exclusive. And it is not about determinism. It's just about affecting the numbers. Okay. All right. So in this example here, a stat class has the following frequencies for the class they're in and the pronoun they prefer. So first year, sophomore, junior, senior. And these were the counts for he, she, and they as their preferred pronouns. All right. So here in this first question, it says find the probability a randomly chosen junior prefers they. So that means we are taking the probability that we are getting someone who prefers they, and I can use T for that, given that they are a junior. Okay. Notice that the phrasing is very important there. It is a randomly chosen junior. So we knew that they were a junior. If I said something about a randomly chosen junior and then started talking about the seniors, that wouldn't really make sense. Okay. All right. So with regard to that, I want to show you this in a chart because I think this makes things super clear about what we're doing. We are talking about only the juniors now. Okay. And in particular, we want the ones that prefer they. There are two of them, and that's out of the juniors. So the juniors, there were, let's see, 2 plus 5 plus 2 is 9. So there were 2/9 of them, which if you prefer to do a decimal, would be about 0.222. Okay, it's 0.2 repeating. All right. So in the other one, we're talking about the probability the person using she. Oh, I can't. Okay, so I'm going to say probability of a sophomore. Can't abbreviate with the S this time. So sophomore, given that they prefer using she, right? So in this case, we're talking about the column of she's because we said we're um, we're choosing from the people who are using she. And we want to then, with regard to that, hang on a sec, let me erase yeah. Let me erase the previous one. Okay, so we're talking about the people who prefer she, and and we want to talk about then the sophomores. There were only 3 sophomores in that group, but it's out of, let's see, 7, 7, 14, right? So our answer on that is 3/14. And if you prefer to use that as a decimal, it's about 0.214. The next digit is 2, so it rounds down. So about 0.214. Okay. So these probabilities, when we're making reference to when we're making reference to given probability, it just means restricting your attention to a certain subgroup. Okay. Hope that makes sense to y'all. All right, so next one, we've got a box of 8 crayons, so 8 different crayons, okay? And you draw one first and another second. So in other words, we're not replacing them. What is the probability the first one is green and the second one is blue? Okay, so we're assuming that we've got green and blue crayon in here because that would kind of be silly to talk about this otherwise. But the probability the first is green and the second is blue. All right. Since these are done time-wise, it makes sense to talk about the probability that the first is green. And since that will change the number of crayons in the box, okay, that means when we talk about the probability of the second one being blue, we need to talk about that given that the first was green. Right? So the probability the first is green is just 1 out of 8, right? You get 8 crayons, they're all different. So we're going to assume then that there's only one of them that's green, and so it's 1 out of 8. Then on the next one, we're assuming there's only one blue one, but it's out of the 7 remaining crayons. And so we end up with 1 out of 56. And if you want to do that as a decimal, then that's about 0.0178. So 0.018. Okay. All right. Yay. So on the next go, we've got a deck of cards and we're going to draw 5 cards. So we're going to ask about what is the probability you draw a flush and the suit matches. We are going to return to this in section 4.4 or 4.5. Okay. The reason for that is that I wrote this question back with a previous version of the book that had the counting first. So we have to do some of the counting tricks in order to be able to talk about this one. So we're going to return to that later. All right, example 4, a fair die is rolled twice. What is the probability that it comes up the same? Okay, so do I still have that in my... Yes, I do. Okay, so we are going to do the same sort of thing as we did previously of just blanking out everything that we've got here in order to talk about what's actually going on. All right. I can't do a very good job of blanking out the blue, I'm afraid. But we can get it out of the way. All right. So then we're going to talk about in these, which ones have it coming up the same. So that would mean like, let's see. this here. The 1 and the 1, the 2 and the 2, and so forth. Okay. So if you're looking at what's going on with that, you have the 2 dice rolls. And what you've got is the probability. Uh, let's say that we refer to those as X and Y. Okay. So the probability X equals 1 and Y equals 1, right? So if you look at that, you're going to see that there is no relationship between the 2 dice. You can roll a 1 and a 5 or a 4 and a 3, anything like that. So knowing the probability on the red die or knowing the outcome on the red die will not tell you anything about the blue die. Okay. So what we'll have then is just the 1 and 6 for the first one and the 1 and 6 for the second one. Because of the fact that they are independent of each other, we can just multiply the 2 probabilities for it coming up a 1 and 1. But so if I'm doing that, I could just paste here, have a copy of it, and change those to be 2 and 2, right? And I'd get the exact same thing. I'm going to say etc. here so that we could have 6 possibilities that would fit this. And so we talk about 6 times 1 and 36th or 1/6. If you looked at the table instead and said, hey, I could just see that I've got 6 of them there and say 6 out of 36 and get 1/6. Totally valid to go that way. The only reason that I said something about this is to try to make that that comparison that we've got 2 events that are happening consecutive in time, but this time their probabilities are independent of each other. Okay. Let me suggest to you a more useful way to think of it also. What we could have said was the probability of anything for the X is 1 in 36, right? And then times the probability that the Y was equal to the X, okay? So that means that for this first one, you'd have the probability of anything. It didn't matter what that first roll was, okay? And then for the second roll, you're getting the probability that it matches the one that you already got. And so we could do the calculation that way as well. In my opinion, this is a more useful way to think about those things, particularly when you're doing card probabilities. Okay. All right. Okay. So here in 4.4, we're going to get to this idea of counting. All right. Now, remember that we said previously, if outcomes are equally likely, the probability of an event, you get it by just counting how many things are in the event and divide by the number of things that are in the sample space. Okay. So then the next idea here is something that we sometimes refer to as the multiplication rule. And it says that if one thing is chosen from M and another chosen from N, then there are M times N results. A quickie illustration of that would be for me to draw another box here. And my boxes are not getting very good on the straight lines. All right. So I'm going to have a box here, and it is going to have 2 rows, and it's going to have 4 columns. So we could real quickly get that this has 8 cells in it, or yeah, 8 spots in it, right? If you look at that and say, gosh, that's obvious, it totally is. That if you were taught multiplication the right way in grade school, this is the way that you tackle things, right? But I do have friends who don't tackle things this way. They just always count stuff. And it seems really weird to me, particularly makes games where we're rolling dice feel really weird and awkward because they take much longer than the rest of us do to count things. All right. But with regard to this, if you're using a TI 80 series calculator, there is a button on there called NPR. I believe that you find that under math and then the probability menu. Yeah, prob menu. I want to say it's down at the fourth or fifth entry on that. I don't have that memorized. Okay. But if you need to do this with a spreadsheet, you do it with this function here. You type the equals and then permut, and then the number of things you're choosing from, and then the number of things that you're choosing. Okay. So we'll have plenty of examples of this here in a minute. But on the other hand, this bit with combinations here, this is when order matters. And the formula you've got for this is more complicated than this one. But if you're using a calculator to get it, you will again tackle it with going to the math menu and then the probability menu and find it in there. Okay. Likewise, the spreadsheets have, oops, I forgot to say equals combinations in choose R. And then I want to make the point real quick that the combinations are the ones that I see the most applications crop up for. Okay. I'm sure that there are permutation applications galore out there, but those are the ones that I see a lot of. All right. In example one, we're going to talk about how many 5-card hands may be taken from a 52-card deck. Okay. So first of all, the fact that we're talking about hands, and I'm implicitly assuming that this is talking about poker or some game that is similar to poker where you're choosing a 5-card hand. If you know something about other hands, you'll realize, I'm sorry, if you know something about other games, you'll realize that sometimes the order that you draw them in might matter. But for poker, you can rearrange them in whatever order you want to, so it doesn't matter. Okay. So I'm going to jot down here that order doesn't matter. Okay. So that means that we are going to be talking about combinations as opposed to talking about permutations. So that means notation-wise, we're going to take 52 things and choose 5 of them, right? Now, I did not grab my HP calculator. Sorry, didn't grab my TI calculator. HP calculator is a different matter. So I'm going to do this all by hand, right? So I've got to say this 52C5, the definition puts the top to be 52 factorial, which is a very large number. I'm not going to try to calculate it, and you'll see why in a moment. And then divided by 5 factorial, and also divided by 52 minus 5 factorial. So 52 factorial divided by 5 factorial and 47 factorial. Okay. Now, I would invite you to pause for a second and go ahead and calculate 52 factorial and 47 factorial and just confirm that those are really big numbers. Okay. But I'm going to try to calculate this without doing that. And so here on my fraction, I'm going to have the 1 times 3 times 2 times 3 times 4 times 5 as the 5 factorial. And the 1 times 2 times 3 times, I don't feel like doing it. 46, and 47. Okay. So I just put a squiggle in there to mean continue the pattern. Then I'm going to say on the top, 1 times 2 times 3 times, I don't want to do it. I'm going to stop though at blah, 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 46, 47, 48, 49, 50, 51, and 52. I should have scooted those back a little bit. As a matter of fact, I think that I will. I just have to grab it and scoot it. Okay. And then I'll put my squiggly line there in the middle. All right. Now, the reason that I wrote it the way that I did here is that I want you to spot that this here, I'll color, I'm going to change that to red. And this here, I'm going to change the color on that to red. Those are the same thing, right? So consequently, if I come along here and just say cancel those things out from the bottom and the top that are the same, this will turn into an easier calculation. Sorry. Equals 48 times 49 times 50 times 51 times 52. Divide by 1 times 2 times 3 times 4 times 5. Okay. So I still don't have my right calculator with me, but these I can punch in fairly easily and do. If you are looking at those and saying, hey, I could cancel some things from the top and bottom, you are totally right. I don't know if it's really worth the effort, but you could do that. Okay. So when I do the cancellation there, I get 2,598,960 as my answer. So this is what I meant in some other example where I said that you could watch people play poker for years and years and never see them draw these super rare hands because there's about 2.6 million different hands that could come up in poker. So, all right. So if you've got that in mind, let's no, okay. Yeah, I want you to keep that number in mind because we're going to jump back later and talk about that example that we had in the previous section. Okay. All right. Here we go with example 2. A person on a restricted diet must eat 2 vegetables, 3 fruits, and 2 breads daily. Okay. At their grocery store, they have a choice of 20 vegetables, 8 fruits, and 5 breads. Just these. This is just a made up problem. So play along with me a bit. Does it matter what order that they do those in? Shouldn't. They, so in this case, order doesn't matter. And that means we're going to talk about combinations. Yeah. Now, we could have talked about it where order did matter for some reason, but I don't think that makes much logical sense here. So that means for their veg choice, they'll have a certain number of possibilities. Their fruit choice, they'll have a certain number of possibilities. And their bread choice, they're going to have a certain number of possibilities. This is applying the multiplication rule. We're just going across there and multiplying. All right. Now, for their veg choice, we can talk about doing that with a choice of 20 things, and we only choose 2. Now, if you want to argue with me and say, hey, they could eat the same veg twice in a day, Yeah, they could, but I'm going to make an assumption here. All right. And then for our fruit choices, there are 8 fruits, and they're going to choose 3 of them. And then for the bread choice, there's 5 breads, and they're going to choose 2 of them. Okay. So if you've got your calculator and you can just tell it to do those, by all means do that. But for my purposes, I'm going to have to go ahead and write this down and have 20 factorial over 2 factorial and 18 factorial. Okay. And on the next one, I'm going to have the 8 factorial and the 3 factorial and the 5 factorial. Notice that the bottom numbers always add up to the top number. And on the last one, I'll have 5 factorial over 2 factorial and 3 factorial. Okay. Now I'm going to, with calculating this, do a little bit of cancellation and have 19 and 20 on the top divided by 1 times 2 on the bottom, and then times 4. And then I should maybe point out that that was for the first one there. And then for the second one here, we're going to come along and say, well, after you cancel out the 5 factorial, you'll be left with 6 times 7 times 8 divided by 1 times 2 times 3. And then the last one, for it, let's see if I can get another color in here. Pink, that'd be nice. Okay, so for that's maybe too pink. So for that one, after you cancel the 3 factorial off, you're left with just the 4 and the 5 out of the factorial, and then a 1 times 2 at the bottom. Okay, so once you've done all that, then I'm still going to end up going to my calculator because I'm lazy. Okay, and I'm going to divide that by 4. So I have ended up with 106,400. Okay. So if you were, I don't know, designing a diet for people that had something like this going on, you could advertise it and say, hey, you have over 100,000 choices on this diet plan. And it would be true. So, okay. All right, example 3. For a certain game, teams of 4 must be chosen with at least 1 child. All right. So maybe you're playing tag or kickball or something, but there are adults and children together in this setup. Okay. So teams of 4, let me highlight that. So teams of 4 and at least 1 child. Okay. And so then we're going to look at, we've got 13 adults and 7 children, right? And how many teams could be chosen? So, looking at that, if we got to have at least 1 child, then let's say what happens when you have 1 child, what happens when you have 2 children, what happens when you have 3 children, and what happens when you have 4 children. Okay, we're just breaking it down into the possibilities. So if you have 1 child, then I'm sorry, I'm going to write across the top, I'll put the child choices, and then I'll put the adult choices. Okay. So if you're only choosing 1 child, then you are in effect choosing doing 7 choose 1, right? And then for the adults, you are taking 13 and choosing 3. And so we'll multiply those together and see what we get. But if you start doing that, you can see how that pattern is going to play out going farther down. Next time it'll be 7 choose 2 times now 13 choose 2. And then 7 choose 3 times 13, choose 1. And then the last one would be 7, choose 4. And then you wouldn't have to worry about the second one, right? So with regard to these, I'm going to have to think about 7, choose 1 as this 7 factorial over 1 factorial, 6 factorial. And the 13, choose 3, I'm going to have to figure as 13 factorial over 3 factorial, 10 factorial. Okay. And I need more space. So pardon me as I take and shove things farther down here so that we have more space to write them out. Okay. So this is going to be the 7 on the top and the 1 left on the bottom after you cancel. Okay. And this one's going to be the 11, 12, 13 on the top with the 1, 2, 3 on the bottom. So if I grab my calculator, just do it. Oops, typed wrong. Yep, I messed up. Sorry. 7 times 13 divided by 6. Okay. So this one will turn out to be 2002. Okay. So on the next one there, and I am going to shove these over a little further to get a little more room. I'm going to need to do 7 factorial over 2 factorial, 5 factorial times 13 factorial over 2 factorial, 11 factorial, which is going to leave me with a 6 and a 7 over the 1 and the 2 there, and a 12 and a 13 over the 1 and the 2 there. And so I think I can just multiply those out. If I can type. I get 1638. Okay. And then for this one here, whoa, I didn't grab the whole thing. All right. For this one here, I'm going to have my 7 factorial on the top. And on the bottom, I'll have a 3 factorial and a 4 factorial. And then I'll have a 13 factorial on the top. And then a 1 factorial and a 12 factorial. So that means on the first one, I will have 5, 6, 7 over 1, 2, 3. And on the second one, I'll have just the 13 over just the 1. So that will turn out to be times 6 times 7 times 13 divide 6. 455 ways that team could come out. And this one here is going to be the 7 factorial over the 4 factorial and the 3 factorial, which is going to have the 5, the 6, and the 7, and the 1, the 2, and the 3. Okay. I went ahead and just canceled the larger number instead of the smaller, in case you're wondering. So, I did it wrong. 5 times 6 times 7 divided by 6. So this is 35. Okay. So if we go ahead and total those up, those different ways of doing things, 2002 plus 1638 plus 455 plus 35, we end up with this plus 35. 4,130 for our final answer there, 4,130. Okay. All right. So the basic notion on that is that we are doing calculations about choosing things, and we're having to consider on it each of our different situations: one child, two children, three children, four children. But all of those situations are mutually exclusive. You can't have one child on the team. You can't have just one child on the team and also have two children on the team. Okay. So we just split those up into a sensible way and then added up after doing each one individually. Okay, example 4, Missouri license plates. I'm originally from Missouri, and this was how license plates were decided when I was a kid. They don't do it the same way anymore, but just trying to make an example here. But so, for instance, the license plates on my first car were TGR 365. Okay. And so when we talk about this notion here, we can figure out the number of different ways that these letters can come out, because we'll talk about each letter and the possibilities there. I should make those wider. 1, 2, 3. And then each number and those possibilities. Scrambling them up in different orders would not make the same plate. Okay. So when we talk about the numbers there, like in the 365, clearly you're going to have 10 possibilities in each one of those, right? Then when we talk about the letters, there is a question: are there any letters that are left out? It might make sense for example, for the letter O to be not considered because it's hard to tell the O from a zero, right? But we were talking about uh, doing this in a relatively simple way. We're not going to worry about that, right? If we have that come up later, we may need to think about it. Okay. But if we go ahead and multiply that out and see what we've got, see, 26 to the third power times 1,000, we end up with 17,576,000 plates. So I don't remember the population of Missouri, but I don't think it's over 17 million. So we really don't need all that many plates, right? But then it says here that additionally, you might have something that's considered a regular plate, a conservation plate, or a veterans plate. So special kinds of plates. So when we take that, we're going to just talk about did it again, 17,576,000 plates. And then you have the 3 varieties on that. So when we multiply that by 3, we end up with 52,728,000. Okay. So we've got nearly 53 million possible tags out there. But of course, we don't actually have all of those because there will be some that are disallowed. For example, if the 3 letters hint at something that's inappropriate, the plates just get disallowed. I had a friend whose name was Stephen Ott, and he tried to get the license plate the personalized license plate SOTT, and he was not allowed to get that because SOT is a British word, which, why would they care about British words in Missouri? But whatever. It's a British word referring to somebody who drinks a lot. So they thought he was referring to drinking, and they thought that was inappropriate. So on the other hand, I saw somebody with a license plate the other day that was 3 letters and much more inappropriate. So anyway, I will let that go. All right, so counting and probability. If we combine together the ideas that we've had here about counting and probability, we can figure out things like the probability of drawing a flush in poker. So a flush means all cards in the same suit. Okay. So when we talk about the probability of getting this flush, we're going to actually talk about it in a little bit more detail. I'm going to put in here and have a heart flush in particular. Okay. And the reason is to make our calculation a little bit easier. So we're going to talk about a heart flush. And once we know the probability of getting a heart flush, that's going to be the same numbers you'd get for a spade flush, a club flush, or a diamond flush, right? So we're going to use this and multiply by 4 to get the probability of getting any flush. All right. So then we've got to say to ourselves, how many card hands did we have? And if you remember, that was 52, choose 5. Okay. Which turned out to be 2 million. Oh man, I don't remember. So let me cheat for a second and jump back here to when we did that one. Where was that? Somewhere in the, here we go. It was in the counting section. So 2,598,960. Okay. So we're going to jump in here, 2,598,960. Okay. But then for the hearts, there are 13 of them. And if we talk about how many different heart flushes there are, that means we are choosing 5 cards out of the 13 there. And so I'm going to jot over here at the side 13 factorial over 5 factorial, 8 factorial, which is going to turn out to be, because again, I didn't bring my calculator, 9 times 10 times 11 times 12 times 13 divided by 1 times 2 times 3 times 4 times 5. So now I've got to go back and get this times 10 times 11 times 12 times 13 divided by, I get 1,287. And if you go ahead and divide that out, 2598960, you get 0.000495. As a matter of fact, if you did that on your TI calculator, it would probably go ahead and put it in scientific notation and say that is 4.95 times 10 to the negative, let's see, 1, 2, 3, 4, negative 4th power. Okay. So about 5/100ths of a percent. So very unlikely. Yeah. All right. But I told you we'd come back to that. We did. Okay. Example 2. A teacher gives 12 question homework and randomly grades 8 problems. I had a friend who would do this all the time. It saved him some grading, and because he was doing random sampling, it meant that he would get roughly the same numbers as if he graded all 12 of them. So you do 10 problems instead of 12 problems. What's the probability that you do all the problems that that teacher grades? So the probability that you do all the graded ones, okay, what you're going to have to do is to talk about, first of all, how many possible ways he could grade it. So he has 12 problems and he chooses 8 of them. Okay. And then out of your homework set, how many different ways could it be done? 10, also choose 8. Okay. So when we do that, I'll bet we can save a little bit of calculation here. 10 factorial over 8 factorial times 2 factorial over 12 factorial over 8 factorial and 4 factorial. Okay, so apologies for doing arithmetic in front of you, but when you divide fractions, you flip them over. And so I can come along with this and do some nice cancellation. The 8s go away. And then do some almost as nice cancellation. The 10 factorial goes away, and you're left with an 11 and a 12. And the 2 factorial goes away, and you're left with a 3 and a 4. So that means that we end up with, oh, wait. That gets even better, doesn't it? The 3 and the 4 go away, and the 12 stays. The 12 goes away, and the 11 stays. So we end up with 1 out of 11, which is not going to divide in evenly, but you will get 0.09090909. So call it 0.091 for an approximation there. So you get a 10% chance of having done all the problems that the teacher was grading. So assuming that he's actually doing it at random. That friend of mine, he didn't actually do it at random. He would pick out the problems you didn't do and grade those. So I don't know why his students liked him. All right. So next bit here. In one of these lottery games, a player chooses 5 numbers from 1 to 10. All right. So chooses 5 numbers from 1 to 10. The lottery commission chooses 5 numbers at random. One presumes that they're still from 1 to 10. So, and if the player has 4 numbers from those drawn, they win $100. Okay. So the probability of winning here, we'll have to look at the number of ways that the lottery commission could do this. And so if they have 10 numbers to choose from and they're choosing 5, right? And then you have to have chosen from their numbers in order to win. Does that make sense? It's not just how many numbers you could choose. You have to choose from their numbers in order to win. So that means out of those 5, you have to choose 4 of them. So then doing this, we will have our 5 factorial over 4 factorial and 1 factorial. And then below, we'll have our 10 factorial over 5 factorial and 5 factorial. So I'm going to arithmetic in front of you again. 5 factorial over 4 factorial, because 1 factorial is just 1. I'm not going to write it again. And 5 factorial and 5 factorial go on top, and then 10 factorial goes on the bottom. Well, I suppose I can do this cancellation here and leave a 5, and this cancellation here and leave 6 times 7 times 8 times 9 times 10. There's probably a little more cancellation I can do, but I think I'm going to just go ahead and write those out. So 5 and 1, 2, 3, 4, 5, and then 6, 7, 8, 9, and 10. So I'll have to go ahead and do that. with parentheses this time, 6 times 7 times 8 times 9 times 10, close the parentheses, equals, I have gotten 0.0198. So I'm going to go ahead and write 198. If you wanted to do that 3 to 3 decimal places, I suppose that you really ought to write it as 0.020, right? So if I were rounding to 3 decimal places, that's what I would say, was that it's about 2%. Okay. All right. So that's the probability the player is going to win that way. All right. In North Carolina, regular license plates have 3 letters followed by 4 digits. Okay. And so that means, if we remember how we did this before, that we'll have 26 to the third, and we'll multiply by 10 to the fourth. Okay. And so I'm going to just grab the calculator here real quick and do 26 to the third times 10,000. And I will get 175,760,000. All right. And then a police officer is operating on a partial plate number. So this means the police officer has some information, but not much. Okay. So we're going to try to figure out what proportion of those total number of tags actually have that. Okay. So if we talk about having an X, but it's only one X, then that means that um, we can have an X followed by 2 other letters, or we can have the X in the middle, or we can have the X at the end, right? And so with regard to those, that would mean that you have one letter decided, and then the other 26 are unknown. Okay, and so when we do that, we have 26 times 26, 676 possibilities. Okay, and then for the numbered portion, you can have the 88 come first, or you can have the 88 in the middle, or you can have the 88 at the end, right? So that means that you've got one possibility where the 88s are, and then the other 2 possibilities, there's 10 in each spot. So we have 100 possibilities there. Since these 2 things are independent of each other, we have 67600. Okay. So 67,600. So if we go ahead and do 67,600 divided by our, what was it, 175, 760, like that. And then we go and do that, 67,600 divide 5,760. Yeah. So we end up with 0.0038. So I'm going to call it 0.004. So it's less than 4/10 of a percent, right? So that's not going to be very many cars out on the road that they'll have to be on the lookout for. If they had more information, like the color of the car or something like that, they could even narrow it down more. Okay. And that is the end of these. All right. And then I stop sharing. Yay. Okay, so hopefully we will be back in class on Wednesday, And for that, we will talk about some more of these, and I will try to answer any questions and maybe give you some sort of a sample exam so that you have an idea of what you're getting on the Monday following. Okay. All right. Hope to see you Wednesday. Bye-bye.